All right, welcome everyone to 9.2. We're going to be doing sum and difference identities today. Again, a lot of chapter 9 is just layering on more and more identities. If you go back to this identity sheet, right? We did the first 5 parts in 9.1. That was, that was that. Today, we're going to spend the whole day on just the sum and difference formulas, all right? And all the things that you can do with these sum and difference formulas. So small note, right? This formula for the sum of angles for sine is one angle plus or minus another angle. And then so there's also a plus or minus here. And that means that if this is plus, then this is plus. If this is minus, then this is minus. Okay? So it's 2 identities in one, essentially. But over here for cosine, right? This is a plus or minus, and this is a minus plus. What that means is that if we're looking at the plus over here for cosine, it's going to be the minus over here in the identity. The minus over here in cosine is going to be the plus in the identity. So this is really telling you that you have opposite signs for the plus and the minus. And if you want to print out your own identity sheet and write on it, you can do that. And if you want to write out the plus one and the minus one separately, you can do that. All right, here it's just written together to save space. It's not intended to be more confusing, but some people have historically not liked it. All right, so anyway. Oh, and then tangent had one of each. Let's actually use them. All right, so example 1. And again, the book talks about where these identities come from, and it's pretty cool, but we're not really going to do it here because essentially, I don't think it's really worth it. There's a lot of cool like theories and proofs. But I don't know. If you're not doing it yourself, I don't think it has that much value. So use the sum and difference identities formulas. This is supposed to say formulas. It's an abbreviation to evaluate the following. So sine of pi over 2 minus pi over 6. So in this first example, this is essentially a useless example. This example doesn't really mean anything. This example is purely to just show you that this formula indeed works. All right? So we promise it works, and let's see it in action. And the reason why this is kind of silly, right, is if we could combine this into one angle. All right? We could just evaluate it with one angle. There's going to be 3 pi over 6 subtracted. If you subtract this, right, this is actually just pi over 3. So we know what our answer should be. If we use the formula correctly, it should be the same as sine of pi over 3, which is root 3 over 2. So let's see if I'm lying to you or whether this formula is indeed true. So the sine of u plus another angle is the sine of the first, cosine of the second, plus the cosine of the first, sine of the second. All right. And one of the best ways to get used to this is just writing it down and using the identity. So it says sine of the first, so the first angle here is pi over 2, times the cosine of the second. Second angle is pi over 6. Oh, also this is the minus 1, right? We have a minus on the inside. Since we have a minus on the inside, it's going to be the same sign over here. Plus or minus means same side. Minus plus means opposite sign. So we know this is going to be a minus sign. So minus the cosine of the first angle, pi over 2, times the sine of the second angle, pi over 6. So that's correctly using the identity. And now we just evaluate all this stuff and simplify and hope that we get the same thing. All right? So let's do it. Sine of pi over 2. Remember, sine of an angle is its y-coordinate on the unit circle. So if pi over 2, right, that's 90 degrees. That's this point up here. This is when x is 0 and y is 1. So sine of pi over 2 is just 1. Cosine of pi over 6. We're going to want to use those reference triangles that I will always give you, right? This is pi over 6, this is 1 root 3, and this is 2. So cosine of pi over 6 is the adjacent over the hypotenuse. That's root 3 over 2. Now minus the cosine of pi over 2. Pi over 2, same angle right here. Quadrantal angles are unit circles. Other angles a lot of times are reference triangles. So cosine, remember, is the x-coordinate, right? We can think about this as x-coordinate. You can think about this thing as the y coordinate. Well, the x coordinate here is 0. So I don't even need to find the sine of pi over 6. 0 times anything is going to be 0. So again, if I wanted to really fill it out, this would be 1/2, but 0 times 1/2, right? This is still 0. So we have 1 times root 3 over 2. And I said, if this works, it should equal root 3 over 2, because this angle right here is just pi over 3. So indeed, I'm not a liar yet. And we've shown that this sine identity works. All right, and we could do this with some more practice, but let's move on and let's skip part B and move on to example 2 and see it in a different format. So find exactly cosine of 75 degrees. And so, okay, all right, let's see, what are our problem solving strategies? If it's a quadrantal angle, then we'll draw a unit circle and look at either the x or the y coordinates. If it's not, we look at our reference triangles and hope that we have a 75 degrees. This is 30, 60, 90. The other one's 45, 45, 90. We have no reference triangle that's going to get this to us exactly. So you might say, well, we can't find it exactly, but we can. Because we know things about 45 degrees. We know things about 30 degrees. And notice what 45 plus 30 is. It's 75. Okay? So this is just going to exactly be the cosine of 30 degrees plus 45 degrees. And by George, we have an angle sum right here. 75 degrees, 30 degrees plus 45 degrees. So we can use this, use our special triangles, and let's see what this is exactly. All right. So first off, we need to use the identity. This time we're using cosine. So cosine of u plus another angle is the cosine of each, and then the opposite sign, so it's going to be minus here, times the sine of each. Or minus the sine of each. So it's cosine of the first, cosine of the second, and then opposite sign, sine of the first, sine of the second. All right. Now we just evaluate. So really, again, for these types of problems, we really only have one step of using the identity, and then it's just evaluating. So again, 30 degrees is pi over 6. Cosine's root 3 over 2, adjacent over hypotenuse. So this first thing is root 3 over 2. Cosine of 45 degrees, again, adjacent over hypotenuse. 45 degrees, adjacent over hypotenuse is 1 over root 2. All right, minus sine of 30 degrees. Opposite over hypotenuse, 1/2. Times sine of 45 degrees, which will also be 1 over root 2. And we just simplify. Multiplying these things together, we get root 3 over 4. Multiply the tops and multiply the bottoms. Minus, not root 3 over 4, right? This is no square root. This is a square root. It's going to be 2 root 2 on the denominator. Minus over here, 1 times 1 is 1. 2 times root 2 is also 2 root 2. So they have the same denominator. We can just combine the numerators. We have root 3 minus 1 divided by 2 root 2. And yep, that's beautiful. That's our answer. That's what this is exactly. If you rationalize the denominator, you can multiply the top and the bottom by the square root of 2. So you could also have written the square root of 6 minus the square root of 2 over 4. This is another answer I would accept. But be very careful. If you write it in this form, these do not combine. The only way we can combine radicals is if they have the same index, so square root, and the same insides. So square root of 6 and square root of 2 cannot be combined at all. So you could express your answer with a rationalized or not rationalized. I'm not going to force you to rationalize denominators in this class, okay? So I'll accept either answer with full credit. So if we wanted to, we could evaluate cosine of 75 degrees exactly just using these identities. All right. And I'm not going to do a part B, but if you wanted to do a part B, right? Cosine of 105 degrees. How could we write this as an angle sum or an angle difference? And a lot of times you're combining either 40 and 45 and either 30 or 60. All right, so if you wanted to use this, you could write this as cosine of 45 degrees plus 60 degrees and do something very, very similar. All right, follow the same steps. And if you want to do this on your own, it's a good idea, good practice. All right, so let's move on to example 3. And again, if at any point people in the who are watching this video live have any questions, feel free to ask. All right, use identities to verify the following. The sine of 45 degrees minus 30 degrees equals the sine of 135 degrees minus 120 degrees. So this is, again, another dumb problem. A lot of the problems in this chapter are really just getting you to flex your muscles. Think of the chapter like this, right? The chapter is less about the chapter is less about doing important things as getting comfortable with your tools. Your tools are these identities, okay? And we're just working with the tools. We're not building anything yet. We'll do that later. So a lot of the problems in this section really are just, can you use this stuff? Is there a way to get your calculator to not rationalize the denominator when evaluating the answer? There might be. You can, there might be. If it is, you'd go to mode and it'd be there near the top on mode. But if not, it's fine. It's fine if you rationalize the denominator. I have no problem with that. So I think it shouldn't matter too much if it doesn't. But if it is important, feel free to let me know. So again, right, this is just saying the sine of 15 degrees equals the sine of 15 degrees. Okay? But we're just going to practice using these identities to show this. So left-hand side, sine of 45 degrees minus 30 degrees. So it's subtraction of sine. That means it's going to be the subtraction version of this. Plus or minus means they're going to be the same sign. So because this is subtracted, this is going to be subtracted. Sine of the first, cosine the second, minus cosine the first, sine of the second. All right. So sine of 45 degrees, cosine of 30 degrees, minus cosine of 45 degrees, sine of 30 degrees. All right. Again, angle difference is going to be sine of the first, cosine of the second, minus cosine of the first, sine of second. And you just evaluate, just like before. Sine 45, 1 over root 2. Cosine 30, root 3 over 2. Cosine 45, 1 over root 2. Sine 30, 1/2, just like before. This is, it's almost, is this the exact same as 75? Did we? Oh, we found cosine of 75. I was like, this looks really familiar. Let's talk about that. Right? Why? Here, let's finish it first. I'm getting excited, all right? Let's just combine this. We did this problem before, essentially. And we're going to talk about why. Same steps as we did in the previous problem. So notice that this is the exact same answer as the one before. So this is the sine of 15 degrees. What do we find over here? The cosine of 75 degrees. 15 degrees and 75 degrees are complementary angles. Complementary angles are just two angles that add up to 90 degrees. Visualizing complementary angles. Complementary angles are just two angles in a right triangle. All right? So, we said the sine of one angle was the cosine of its complement. That should be familiar. Cofunction identities. The sine of one angle is the cosine of its complement. 75 degrees, 15 degrees. They're equivalent. So it's all coming together. Yeah, I've had this binder since I was in high school. I think it's not as dirty as it looks. It has like ink stains, but on the camera, it looks disgusting. I should probably change that. Anyway, so that's the left-hand side. Now we do it again for the right-hand side for some more practice, and hopefully the right-hand side equals the same thing. Okay. All right, what do we got here? The sine, again, is going to be the sine of the first, cosine of the second, minus sine of the cosine of the, goodness gracious. I can't say it, write it down. It's going to be the same formula, just instead of 45 and 30, it's 135 and 120. Okay, so we're going to have the sine of 135 degrees, cosine of 120 degrees, minus the cosine of 135 degrees times the sine of 120 degrees. And hopefully, oh my word, look at that, we got a little double degrees right here. Now, hopefully, we'll come to the same answer. So, these are very similar, and it's going to be helpful to plot these, right? 135 degrees is in the second quadrant with a reference angle of 45. It's going to be negative 1, 1, root 2. This is 135 degrees. And again, the x component's negative, so we're going to call this side negative. 120 degrees is 90 plus another 30. It's going to have a reference angle of 60 degrees. So it's going to be negative 1, root 3, and 2 using our reference triangles. And again, the x component's negative right here. All right. Also, my camera settings have the contrast turned up. I turned up the contrast so the letters and the writing would, yeah, it is what it is. So the sine of 135 degrees, opposite over hypotenuse, 1 over root 2. Cosine of 120 degrees, adjacent over hypotenuse, negative 1/2. Cosine of 135, negative 1 over root 2. Sine of 120, root 3 over 2. So we have a negative times a negative. That's going to become positives. This one multiplies to negative 1 over 2 root 2. This one becomes root 3 over 2 root 2. And look what happens when we combine them. This minus that is what we get. Root 3 minus 1 over 2 root 2. And notice that the left-hand side was this. The right-hand side is also this. Yeah. They're equal. Left-hand side equals right-hand side as desired. And then we can do a check mark. You can do a smiley face. You can do a thumbs up. If you know how to draw one, that does not look like a thumbs up. Hold on. I'm glad you guys didn't see that. That was off camera. I tried to draw a thumbs up and it looked like something else. Anyway, we're okay. You don't subtract the denominators when you combine fractions. You only combine the numerators right here. Yeah, exactly. Proving that sine of 15 and sine of 15 has never been easier. Yeah, preach it. The wonders of mathematics. All right. Oops, I changed my scene. I lost the camera. Okay. Let's do another one. All right. And honestly, though, that's a good question. That's a good question to ask, because really it illustrates that one of the hardest things of this section is really the algebra. It's essentially using the trig identities, evaluating some things, and then just a lot of algebra after that. Okay, let's really take this up another level. You guys are gonna like this problem, I promise. Find exactly. Okay, so find the sine of the inverse cosine of 1/2 plus the sine of inverse, plus the inverse sine of 3/5. So this looks like garbage, but it's okay. And you don't need to use trig identities if you just want to approximate this. If you want to approximate this, you could type this in your calculator, no problem. But if we want an exact answer, trig identities are going to come real in handy. So Remember that even though this looks awful, this is just an angle. That was one of the big things we talked about from 8.3. Inverse trig functions spit out angles, right? This is some angle. Maybe we call that angle U. This is some angle. We call that V. These are angles. So we're just asking, what is the sine of this angle plus another angle? Well, let's use an identity. Because once we use an identity, right? If we forget about the plus, we did problems exactly like this in 8.3. All right? And that's what we're going to break this down to. So we have sine of an angle plus another angle. So that's going to be sine of the first. Again, you just go back to your identity sheet. You don't have to memorize them. Plus inside means plus outside for sine. Sine of the first, cosine of the second, cosine of the first, sine of the second. All right. So here we go. We're going to have sine of inverse cosine of 1/2. This is the first angle, right? And if it helps you with U's and V's, go for it. All right. Sine of the first angle, cosine of the second angle. What is our second angle? The inverse sine of 3/5. And then it's going to be the same sign, so plus here. Now it's going to be cosine of the first angle. First angle again is inverse cosine of 1/2 times the, oh, I don't have room for this, times the sine of the second angle, which is inverse sine of 3/5. So again, notice, we said sine cosine plus cosine sine. And the first angle, yep, first angle, first angle. Second angle, second angle, second angle. So we know that we're plugging this in correctly. And now, this is where things get great. You get to do 4 8.3 problems at the same time. So that's how math works, right? You're always building on other stuff. You're building on what you've talked about previously. So if you don't understand 8.3, this is going to be a little harder. But we got some good news for you. Let's start with the easy part. All right. Remember that we said that these usually cancel out as long as we're in the range. And really, that only matters if it's flipped. If it's in this order, they always cancel out. So let's do the easy part first. Cosine of the inverse cosine of 1/2 is 1/2. Sine of the inverse sine of 3/5 is 3/5. Ah, great. So as long as what's on the inside is correct, and again, if the functions are in this order, it always will be. If it's the other order, the angle just has to be in the right quadrant. They cancel each other out perfectly. So now we got to do the harder part, right? We got to do this part. And there's easier ways to do this and harder ways to do this. But one way to do this is to draw a triangle. Okay? First triangle, we need to look at this angle. We need to look at an angle so that the cosine of that angle is the adjacent over the hypotenuse is 1/2. And we know this triangle. This is actually a very special triangle, but even if you don't, it's fine. You need to use the Pythagorean Theorem to find this other side if you don't know this triangle. But the important thing is that we don't even need to know what theta is here. Okay? Spoiler alert, it's 60 degrees. But we don't need to know that for these sorts of problems. Pythagorean Theorem says 1 squared plus b squared equals 2 squared. Solve for b, you're going to get the square root of 3. So either way, it doesn't matter what this angle is. I called it u up here. I called it theta here. Doesn't really matter. We care about the sine of that angle, root 3/2. All right, so this first thing, this 8.3 problem, becomes root 3/2. And then we have a second triangle situation over here. We need to look at another angle. Let's call it, I don't know, phi or v, if we're really trying to be consistent. And whatever angle this is, right, this is just some angle, we're looking at what is the cosine of that angle. So in this triangle, the sine inverse of 3/5 is the angle. That means sine of that angle is 3/5. And again, use Pythagorean Theorem, you're going to get 4. Right? You'll set it up as a squared plus 3 squared equals 5 squared. And I trust you all to be able to do the algebra to solve that. And you're going to get 4. 3, 4, 5 triangle, 30, 60, 90 triangle here. So either way, the cosine of this angle adjacent over hypotenuse is 4/5. So it's kind of spread out because we did a lot of simplification right here. Let's see how it simplifies. The first fraction becomes 4√3. Again, not radical, radical. They cannot touch. They're just multiplied by each other. Divided by 2 times 5, which is 10, plus 1 times 3 is 3, 2 times 5 is 10. Same denominator, so we're going to add the numerators together. But just like last time, the numerators don't combine. We try to combine them, but this has a square root of 3 and this doesn't have a square root of 3. So that's as simplified as it gets. And this is what this is exactly. 4√3 plus 3 over 10. So we used one identity from 9.2, and then we got 4 8.3 problems. All right. So you have an exam coming up that has 8.3 on it. Good idea to review if you're rusty on 8.3. No, you cannot combine these. The only time you could combine these is if you had something like 4√3 plus 3√3. Because then that would combine to 7√3. Think of it like this. Think of radicals like variables. What we have up here in the numerator is kind of like 4x plus 3. These can't combine at all because this is missing an x. It's the exact same situation. So this is not 7x, for example. All right, and that's a lot of times how you can think of it. Just like when we multiplied, it's like multiplying x times 4 is just 4x, which is exactly what we have right here. Kind of the same logic. Thanks for asking the question. All right, that's essentially what we have here in example 4. So it's at this point where you're probably saying, okay, you said we're going to talk about sine, cosine, and tangent. I'm really itching. This tangent one, this looks good. This looks like a fun time. Why aren't we talking about it? Well, all right, it's time. So tangent's tricky because it's pretty messy. And also because, again, plus or minus, that means same sign. Plus or minus, minus plus, that means the opposite sign. So if this is a plus on the inside of tangent, the top will be a plus, but the minus will be a minus. The top, let me try that again. The top will be a positive, the bottom will be a negative. So it's really easy to make mistakes on this. And again, on your own identity sheet, both in my face-to-face class and my online class, you can print it out. And you can write both of these separately. The plus one and the minus one separately on your identity sheet. I will let you use that for quizzes and exams, all right? So you can write things on this sheet that you can still use for quizzes and exams as long as it's appropriate stuff that you're writing down and not like, I don't know, some kind of cheat. But you can write identity stuff down. And if you're ever worried about what you can write down or what you can't write down, send me an email or ask me in class. All right. Anyway, here we go. Let's do example 5. We'll do example 5 and then start example 6. And I think that's where we'll call it for today. So in example 5, we've already been going for 30 minutes or so. All right. In example 5, find exactly. We're going to do essentially what we did for example 1, where we use the identity where we didn't need to. And the idea for this is to give you some sort of intuition. Actually, we do need this, right? This is 75 degrees, 30 degrees plus 45 degrees. So it's not like example 1. I lied to you. Forgive me, please. We're just going to use the identity. So we can solve our identity sheet and don't get overwhelmed. All right, plus or minus. I switched scenes right as my cat just walked right over my math. If it's plus here, it'll be a plus on the top and minus on the bottom. Whatever's on the top is the same sign as the inside. And whatever's on the bottom is the opposite. So it's going to be something plus something on the top and something minus something on the bottom. Same sign on top, opposite side on bottom. And the identity said the tangent of the first plus the tangent of the second. So it's going to be tan of pi over 6. And over here is going to be tan of pi over 4. All right. And in our denominator, it's going to be 1 minus the product of the two tangents. So 1 minus tangent of the first, tangent of the second. So there, even though tangent looks messy, right? This looks kind of awful. We really only have to find two things this time, right? If we used the cosine identity or the sine identity, notice, right? We had to evaluate 4 different trig functions. And here, even though it looks kind of ugly, there's really only 2 different functions we have to evaluate, tangent of pi over 6 and tangent of pi over 4. So we do have that advantage for tangent if you want to, look at silver linings. So again, we have to consult our 2 triangles that we're going to use all the time. Oh, my cat's in my lap now. I wish I could lecture in my face-to-face classes with my cat in my lap. I think that would be a lot more fun for everyone, except for those who are allergic to cats. It would not be very fun for them. All right, so let's use these triangles. All right. Exactly, yes. You can't cancel the top and the bottom because of the addition and subtraction. If you have addition and subtraction in fractions, it makes your life way worse. So we need tangent of pi over 6, opposite over adjacent. That's going to be 1 over root 3. Oh, we're going to have complex fractions here. This will be fun. Plus tangent of pi over 4, opposite over adjacent. 1 divided by 1. All right. So this is nice. Tangent of pi over 4 is 1. That's going to make our lives a little easier. And the bottom is 1 minus tangent of pi over 6, which we already said was 1 over root 3, times tangent of pi over 4, which we already said was 1. So let's simplify this as much as we can. Really, there's not that much to do yet. Right? This multiplying by 1 essentially doesn't matter, but this is still needs to be simplified. This looks awful. And again, even though the top almost looks like the bottom, we can't cancel because they are not exactly the same. If we could factor it, yeah, then maybe. So we have a complex fraction. Complex fractions are not simplified. We need to simplify the complex fraction. And there are 2 ways to simplify complex fractions. The first is to take the top and multiply it by the reciprocal of the bottom. That's very dangerous because the reciprocal of the bottom, we don't know that. We can't find the reciprocal of the bottom unless we combined the bottom fractions. So the easier way a lot of times is to multiply the top and the bottom by the LCD of all the fractions. So luckily, we only have one denominator. So to get rid of that denominator, all we have to do is multiply by the square root of 3 over the square root of 3. And then remember to distribute on the top and distribute on the bottom. And that'll probably make things look a lot nicer. No promises. I don't know where this is going, but I have faith. And I've done, problems like this. So when you distribute it in the first one, we get the square root of 3 divided by the square root of 3. That's just 1. When we distribute to the second one, we get 1 times the square root of 3, which is the square root of 3. Yep, already looking better. The bottom, distributed over here, we get the square root of 3. Distributed to the first one, the square root of 3's cancel, we're just left with 1. And I know this is going to drive people crazy, but nothing cancels here. And again, I said I'm not going to make you rationalize the denominator, so you don't need to. I would accept this answer. But if we rationalize the denominator, it will look a lot nicer. So if the denominator is just 1 square root, it doesn't really look nicer one way or the other. But if the denominator is like a square root and another number, rationalizing makes it look a lot nicer. So let's just keep going. All right. Remember, so to rationalize the denominator here, we have to multiply by the conjugate of the denominator. I don't know if anyone's going to remember this, but that's what we do. So we're going to multiply by the square root of 3 plus 1 divided by the square root of 3 plus 1. Again, conjugate just means the same thing that's in the bottom, but the minus becomes a plus, or the plus becomes a minus. It's almost the same thing as the denominator, but you just switch the sign in the middle. And then what do we have here? Wow. We get to FOIL. This is a problem that kind of keeps on giving. Maybe this is what we'll call it. Yeah, this will be our last example. This one just keeps on going on. So if we FOIL in the top, The top, we can actually take a little shortcut if you know shortcuts, because 1 plus the square root of 3 is the same as the square root of 3 plus 1. These two tops are the same. These two tops are the same. So if you know the formula for perfect squares, you can FOIL it out that way. But if not, you can do it. So normally I'd go to the next paper right here, but because we're really FOILing this out, it might be helpful. Oh, my head's blocking it, to just see it right here. So our top is 1 times root 3. That's root 3. FOIL is first. Outer, 1 times 1 is 1. Inner, the square root of 3 times the square root of 3 is the square root of 9. Square root of 3 times the square root of 3, you multiply the insides. And then last, square root of 3 times 1 is square root of 3. In the denominator, we have the square root of 3 minus 1, square root of 3 plus 1. This is difference of squares. We can take a shortcut. If you want to FOIL the denominator, be my guess. But let's take a shortcut. Difference of squares says it's going to be the first thing squared minus the second thing squared. So square root of 3 squared is the square root of 9. 1 squared is 1. All right. So now we just simplify. We have the square root of 3 plus the square root of 3. That's not square root of 6. Think of it like x's. X plus x is going to be 2x. Similarly, square root of 3 plus the square root of 3 is going to be 2 square roots of 3 now. And the square root of 9 is just 3. So 1 plus 3 is 4. What about our denominator? Square root of 9 is 3. 3 minus 1 is 2. Ah, we're almost done. The top and the bottom are both divisible by 2. Okay. So let's divide the top and the bottom by 2, just like we're reducing. If we divide the top by 2, let's start with the bottom, that's easier. If we divide the bottom by 2, we have no bottom. Dividing by 1, done. If we divide the top by 2, we just have the square root of 3 plus 2. This divided by 2, the 2's cancel. This divided by 2, we just have 2, and wow. There you go. That's the tangent of 75 degrees. So that was fun. And again, here's my point, right? We did one step. One step, that's 9.2. One step, that was an identity. After this very first step, that's not chapter 9 at all. This is chapter 7, right? What is the tangent of pi over 6? What's the tangent of pi over 4? Then it's essentially hard algebra. Get rid of the complex fraction. Rationalize the denominator. Simplify. FOILing. Algebra will kill you in this chapter. All right? So don't be afraid to brush up on it if you need to. Complex fractions and rationalizing the denominator, FOILing, factoring. Those are really the 4 big algebra things that you're gonna need to be comfortable with in this entire chapter. All right. And yeah, go ahead and check it with your calculator. Something, small note, so in 8.3, I said you can use your calculator for anything. In chapter 9, though, you can use your calculator to check your answer, but I will be requiring you to use the identity. Because in stuff like this, I don't care about the answer. Finding the tangent of 75 degrees, I couldn't care less. What I do care about is, can you use this identity? All right. So essentially, and I'll talk about this in class tomorrow as well, for those in my face-to-face class, is you can kind of use both, and people have been doing that quite well, which is very happy to see. I am very happy to see that. All right. So what we're going to do tomorrow, next week, I guess. Yeah, what we're going to do when we finish the section next week, we're going to do some more fun stuff. I really like example 6. Example 6 is going to look way quicker than it actually is. And then we're going to verify some stuff, which will be pretty straightforward, and do a couple applications. All right. Anyway, thanks for watching. Hope you enjoyed the video. Feel free to email me if you have any questions.